Yep. Hello, everyone. Thank you for coming to our BlinkOn talk. It's a pleasure to do this our first time, our first year here. Yeah. So our talk's mainly going to be on the privacy API protections in Chrome, and my name is John. I will be working on the canvas interventions work for the past about half a year.
I'm Tanushree. I've been working on the local fonts intervention, and that's just mainly been getting started. So we're very excited to be there.
And yeah, so we're on the Chrome Privacy Sandbox team and mainly the anti-fingerprinting team. So if you imagine a world without cookies, how exactly would you like identify users? And the main way to do this is really just to get a stable output from all these different web APIs. And these web APIs can vary based off of like what browser you're using, what device you're using, and so on and so forth. And if you take all these different variations and kind of combine them together, you'll essentially get some sort of stable output. Yeah, so some of these types of data can include user agents, languages, Chrome versions, device types, et cetera. These are all, so the output of these APIs can all vary based off of like, your device or your Chrome version, so on and so forth. And essentially, if you try to combine all this information together, then you can actually get a somewhat stable identifier. We'll say fingerprints. We're not really allowed to do that, but anyways, so this measurement of information is what we're going to call entropy. And then essentially the bits of entropy is essentially the unit of this measurement of information. So over on the right here, you'll notice that like we have an array that looks like n bits. This n value is actually left ambiguously or left purposely ambiguous, because it really depends on the population of that region. So I think most of us like didn't get the first part, so I need to start over. We just like okay. Try to like give a quick TLDR what we just covered. Like
sure, don't worry. Vanguard is sending response to debates.
Yeah, so for those of you that missed it, the TLDR here is basically like if you get a bunch of web APIs that have a variation in different types of values, depending on your Chrome version, your device, et cetera, and then kind of combine these together, you would get some sort of stable identifier that's unique to you, right? Instead of using a cookie. But yeah. Okay, so we have like a nice little diagram here that explains what entropy is at like a high level. So on the left here, this API values are basically based off the cookies enabled value here. So let's say I enabled cookies, and then we have this one person that disabled cookies. If I enabled cookies and I was in this like top partition set of users, and let's say Tanushree here was a tracker, it's not really useful to her where I am in this left side here, because like there's 30 other people that also have cookies enabled. So that's not really like useful information, but it still has some variation here. So medium entropy, on the other hand, is basically if we partitioned these values even more. So let's say languages, for example, we have, this top half of people using English, the other top half people using Hindi, and then we have Russian and Spanish, and so on and so forth. If I was using English, then the other bottom half that use Hindi or Russian, Spanish are basically all irrelevant in that case. And we know as a tracker that I will be in that top set of English users. So now when we get to high entropy, we actually have like a whole bunch of other devices, right? So like Galaxy S8, Galaxy Note, Pixel, so on and so forth. Let's say I was using the Galaxy S8 in this particular case, then I'm now down to two of the users here, the top two Galaxy S8 users in this particular case. So if you essentially combine all this, like we have the low entropy, the medium entropy, and the high entropy, chances are I will be quite unique amongst the Galaxy S8 users, right? Maybe the other Galaxy S8 users using Hindi, or maybe they have cookies disabled. In that particular case, then it kind of narrows it down to me. So basically TLDR, if you have higher entropy, it's actually easier to distinguish users. And therefore it's less private. If you have lower entropy, it's harder to distinguish users, and therefore it is more private. So yeah, this n bits that you see here essentially is the number of bits that you need to essentially uniquely identify and this n is kind of dependent on the population of web users. So in this particular case, we noticed that this n bit kind of correlates with 2 to the n web users. So let's say I had 16 web users in this particular case, then it really only needs what, like 4 bits of entropy to essentially get some sort of stable identifier. So all these different web APIs essentially can leak, a certain number of bits of entropy. Canvas and fonts may have overlapping pieces of data, but essentially the idea here is to kind of fill in this entire array to get up to n bits, and in that particular case, you can get some sort of stable entropy. So this talk really isn't about entropy, and so if you are really interested in what this is, feel free to take a look at the Assessing Web Fingerprinting Risk. Some of the early contributors for the anti-fingerprinting work have authored this paper. So we're going to talk a little bit more about reducing canvas entropy. So what we noticed from the coveryourtracks.org sites, you can actually leak up to 8 bits of entropy from canvas elements. And the types of data that you can actually retrieve are browser type, your browser version, the platform architecture, the rendering engine, so on and so forth. But most importantly, you can actually get the GPU information, because essentially what a canvas is really just an image that you're rendering onto your browser. And then little variations in that output can actually leak certain types of GPU information. So in this particular case, maybe your device type and whatever drivers that you're using. You can actually typically combine this with like fonts or any other web APIs, and then essentially you can kind of just fill in the arrays until you get to the n bits that are required to generate your stable output or your stable unique identifier. So on the right here, you'll notice that there's a snippet from BrowserLeaks. BrowserLeaks is a quite useful tool. It basically shows you your canvas fingerprint, your signature, how unique you are, what types of data you're leaking. Obviously, I had to opaque my signature. I don't want you guys to review, but yeah, but feel free to try it out yourself. So basically, how exactly can we get a canvas fingerprint? Pretty much what we want to do is, render a couple images. The shapes can be different, the colors can be different, so on and so forth. Maybe have some text here and there, and then convert this data into some sort of digestible form. And so mainly there are 2 APIs that we're targeting: is the toData URL and the get image data APIs here, or operations here. And then lastly, most fingerprinters end up like hashing this data to get some sort of stable identifier. And then in that case, they can kind of share this across different sites and then essentially track your usage. So an example here, we have device 1 and device 2, and to us, they look exactly the same, but to a machine, it might look slightly different, right? The pixel values here in the bottom right, you can notice that like the top left pixel here is 255, 145, 145 in device 2, and then the device 1 will actually have this on 255, 200, 200. And these little variations in the rendering process essentially is kind of what distinguishes different graphics drivers, graphics cards from rendering these images, right? So anyways, we noticed that a lot of fingerprinters end up doing this, and how exactly do we want to stop this? You essentially want to tamper with the readback operations. So toData URL and get image data. They are responsible for reading back all the pixel data from the browser, and you can share that across different sites and so on. Okay, so now we're going to talk a little bit more on implementation details. So it's quite small, and I'm sorry I couldn't really fit everything into one slide, but the top left here, we have more of the browser-sided operations, and in the bottom right here, we have more of the render-sided operations, and namely in Blink. So if we talk a little more about the browser-side stuff, we have something called noise tokens, and essentially what noise tokens are 64-bit random numbers associated per browser context. And what this essentially means is that if you open an incognito browser versus a normal browser, these 2 browsers are 2 different browser contexts, and they'll generate 2 different random numbers. And so why is this really important? It essentially adds a randomness to our deterministic hash, and this hash is basically the basis for the noising algorithm that we have. So you can think of the noise hash as a function of the noise token plus the top level site that you're on. And so what you will expect here is that like if you have 2 tabs both on CNN.com in the same browser, you'll expect the same noising pattern in both sites. But let's say I open CNN.com on an incognito browser. In that particular case, then CNN.com on incognito versus CNN.com on the normal browser will have 2 different canvas noises, or the noising output. Essentially, your canvas fingerprint will be different in both cases. So how exactly do we do this? We leverage something called the render preferences, which is essentially an early Mojo pipe. that will send the noise token before any JavaScript loads. Render preferences are quite useful for other cases, like whether or not you want to change the rate of whether your cursor blinks. Not the blink render engine, just like the action of blinking. But yeah, so the noise token is pretty simple. It's just a 64-bit random token, so it's just a UN64 that you pass down to the render in this case. But the most important part is that it lands before the JavaScript loads. If the JavaScript can run before the noising actually happens, then it's practically useless. Noising is practically useless. So what we added here is a new process local global value that is for each new render frame. So it's a new addition in the third-party Blink public directory called the canvas noise token. Feel free to take a look. You have access to the slide deck. So that's how exactly are we going to determine browser activation? So we leverage something called the Blink runtime enabled features, and essentially these are basically like true or false switch feature flags that can be overridden at runtime. And so if you, let's say in the browser process that you have like some sort of user bypass and want to disable this feature flag temporarily, and then reflect down to the render, you would use the Blink runtime enabled features, and they're quite popular. So we essentially leverage this as our master activation here. So before any noising happens, we would essentially check if the browser activation worked or is enabled. And how we determine whether or not we want to enable the canvas interventions flag is the combination of the Finch states that we have, the Finch state, and we're going to call this the canvas noise feature flag. Whether or not we're in incognito, and whether or not we have any exceptions, like URL level exceptions or user bypass, so on and so forth. Yeah, so how Blink runtime enabled features work, we essentially use something called the commit navigation params. And basically this is a multiply that overrides the feature flag values in per navigation into the render process. So we have naturally we would have a new web contents observer called the interventions web contents helper. Basically sets the override states of the canvas interventions flag, and then we set the state before we commit any navigations, and then once we commit navigation, the render process should have this updated value. Okay, so now we're going to talk a little bit more about the render process here. So generally, you can imagine that noising is quite expensive. We have to copy the canvas, and then we have to perform operations on each individual pixel, and then recopy it back into the readback operation. So we need to be absolutely sure that we are noising a potentially fingerprintable canvas. We can't just keep noising like every single canvas. That would be a performance disaster. But essentially, how we determine this is essentially we have a bunch of function hooks that record whether or not like critical canvas operations have been called. So some of the functions that we've noticed from notable trackers is that the arc, ellipse, stroke, fill text, stroke text, fill rect, and then so on and so forth. There's many more I couldn't list. Essentially, if these get called, then that's one of the many heuristics that we use to determine whether or not we should activate noising. The other one here is that whether or not the canvas is 2D, and then mainly whether or not it's in the GPU context, right? So mainly because canvas leaks out GPU information, we want to be sure that we're only noising on GPU rendered canvases. There is a way to do it on CPU rendered canvases, but it's irrelevant for this particular work right now. And then lastly, we need to have this master flag from the browser activated in order to activate noising in general. So yeah, so it's enough talking. I guess I can actually show a quick demo on this working. So this got released last week on M136. Let's see if I can present this. Okay, so this is M136 on Chrome Canary. So you notice here the hash values of these two images are, so these two images are exactly the same, right? But the hash values are exactly the same here. So if I went on a different websites with the exact same images, the hash values are the same. So I basically just fingerprinted myself here using Canvas. But if we turn on the Chrome flag, it says enable noise for Canvas readbacks in incognito. If I enable it for all browsers, hopefully relaunching it doesn't. Okay. Let's see if you do entire screen instead. Okay. You notice that these values are now different. And so if you go on this website too, the values are now different between the noise and the unnoise. And more importantly, the noise versions of website 1 and website 2 are now different. So now if I went to incognito, open up the same site, you should now see a different hash value as well. So this is the noise token at work here. The hash value is slightly different, is different in the unnoise version here, but that's mainly because this website has to read back twice, and so if we're noising it twice, then the hash value has to be different here. But mainly this works, and you can try this out in Chrome Canary, and then file any bugs. Here, let me see if I can. Okay, so a little more information. Okay, this is just in case that the demo didn't work, but we do have an explainer for Canvas. It's linked in the slides, and then we also have another talk on the noising algorithm itself. It's a learning talk by one of our contributors named Tom. If you want to follow the code, search up the fpf-ci change list text, and then you can see all the contributions that we made. And try it yourself on Canary, right? Enable the Canvas a noise flag, try out the test sites, and then go into the wild and see all the different canvases you're ending up noising. And then if you see anything weird, feel free to file bugs, and then they'll help us debug a lot of our stuff. So I will head it off to Tanushree.
Cool. Thanks, John. So yeah, I'm Tanushree, and I'm working on the local fonts intervention. So essentially, we're trying to access to user installed fonts in Chrome. So as an overview, fonts can actually present identifying information about the client, as we've seen in a previous slide that discussed entropy. So that could be information such as the device type, the browser, the language set that a user has installed in their device. And oftentimes the combination of fonts installed on a device can vary significantly between users. So as a result, trackers may actually take advantage of this and make scripts that are able to re-identify users across context using fonts. So the goal of our intervention is actually to improve user privacy by restricting the availability of user installed fonts on Chrome. And as I mentioned before, there can be differences in how text is rendered across platforms with the same font. So here you can see in Mac OS and Windows, there's some slight variation. Even on the same device here, with different platforms, you see like how the font or the text rendered looks different. There's slight differences in width, etc. So beyond improving privacy for the user, we've had several reasons to motivate this effort. So over the years, the CSS working group has had ongoing discussions on local font issues. So there are various implications on IETNN support on the web, and also like how we balance that with the privacy needs. And also a more recent CSS working group discussion has brought up the idea of prescribing user agents to not display user installed fonts on the web as a privacy protecting measure. And this kind of mirrors Safari's approach of limiting to the OS shipped fonts list by default. And so we've also noticed that other browsers like Firefox and Brave have also implemented measures to prevent access to all the full set of user installed fonts. So as mentioned before, trackers can use fonts to identify users, but specifically they may do this by indirectly testing for the presence of a font by measuring the size of rendered text for fonts that are being probed. So for example, you may want to measure the width of a span that's invisible of a font in question, or you may draw some text on a canvas and measure that text. And essentially the way we do this is we do this repeatedly for a large set of fonts or particularly important fonts that can be identifying to user. And then we compare that to the measurements of fallback fonts. And if we quickly do this, we can build some sort of signature or get some sort of idea of the set of fonts installed on user system. So trackers take advantage of this, and this is why we're trying to implement some privacy protecting measures. So there are various ways we can set or access local fonts. So the most popular way is the CSS font family property. So here we have a font fallback list, which is evaluated from left to right, with the rightmost font being a generic font, sans serif. There's also the local source to the CSS font face rule. We also have the font property of the canvas rendering context 2D. And we also have the local fonts access API, which we're not going to intervene on, but we are factoring this into our intervention. So essentially, the local fonts access API allows a web page to kind of get access to the full set of fonts installed on a user's device via the window.query local fonts method. However, when that happens, the user gets his permission prompt. And if they allow it on the origin, the web page is able to get the set of local fonts. So essentially, we want to honor the permission that is granted by the user in our interventions. So our intervention is actually in very early stages. We're kind of trying a phase-by-phase approach where we first start with experiment analysis to see whether we can start in incognito mode and then potentially expand to normal browsing mode. So there are 3 major steps that are involved. So first, we're going to think about how we're storing the list of OS shipped system fonts. So initially, we're starting off with Mac OS and Windows as our platforms because they've already published their list of OS shipped fonts online. And then in the Blink renderer code base for fonts, we will filter the non-OS shipped fonts from being selected from rendering. And in addition to the actual filtering mechanism, we will gather metrics in normal browsing mode because we will have a higher sample rate there. And that will help us inform our decisions to move on to the next phases of the project. And as mentioned before, we will gather these metrics and perform experiment analysis. So John actually touched on this in his talk on Canvas about how we activate the intervention for Canvas. So we follow a similar infrastructure, but for the local fonts intervention. So we're going to use a Blink runtime enable feature that's activated from the browser side. And the criteria is different here. In addition to the Finch flag, we will look at whether we're looking at a Mac OS or Windows platform device. And we also want to check the permission potential permission granted from the local fonts access API. So essentially, we're just honoring whatever the user said to that permission prompt if it was displayed at all. So here's kind of like a mini snippet of what the intervention would look like. Obviously, the actual intervention will look different because we will have more code paths where we're collecting metrics on the impact. So here we see we're in the font fallback list, and we're first starting off by intervening on the CSS font family property method of accessing local fonts. So essentially, when we see that we've run into a successful font family match, we want to check whether it's a local user installed font or essentially a non-OS shift font. And then if it's not, then we will essentially allow it to be used for rendering. So from the metrics we collect, we want to perform some experiment analysis. So we're quantifying impact on font fallback rates. So essentially, we want to see how many times we're running into the last selected font as a result of this intervention. We want to see performance impacts. For example, like the filter mechanism will add some latency, so we're trying to get an idea of what that is. And we also want to see the impact on less common languages, such as non-Latin languages. Fonts are less available for those types of languages because they have complex or rare script that may not have full Unicode coverage. So these could be CJK languages or like stuff like Arabic or Aramaic scripts. And the goal of this is to adjust our reference font list for better coverage. And also we want to see whether we can expand this intervention to more users. And as mentioned before, various challenges we face are particularly with non-Latin scripts. So we want to be able to make sure we can accurately gather metrics given the different code paths in the Blink fonts rendering code base. And we also want to make sure that we're balancing the privacy needs while also making sure that IAT needs are also not disproportionately impacted. Platform level differences also was a challenge to consider. So different platforms have different font caching and fallback mechanisms. So we need to consider all those differences because attackers may consider circumventions against our efforts. So we kind of need to play like a cat and mouse game there. And also we need to think about how we're going to source and maintain these OS shift font lists in the future in a more accurate, up-to-date manner. So looking forward, as I mentioned before, We're actually in early stages, but as of last week, we just published the fonts explainer. So feel free to check it out on GitHub. And we also sent out an intent to prototype. So we'll be starting on the dry run experiment analysis soon. And if that goes well, we'll think of shipping in incognito, where the user has explicitly or implicitly signaled that they care about privacy. And if that goes well, in addition to looking at the metrics that we get from our dry run, we may consider the potential for expanding to normal browsing mode as more of a platform hardening and web standards conformance measure, given the CSS working group discussions that have happened as of recent. And we want to also improve how we're sourcing those OS shift font lists. So we may need to collaborate with those platforms so that we can receive timely updates of those lists, and maybe see if they would like open up some sort of API that would allow us to programmatically access those. And as we've mentioned several times, we want to think about improving support for non-Latin languages. And as a conclusion, the main effort of these, so the main goal of these efforts is to make it more difficult to extract entropy and improve privacy for users cross context. For Canvas, we do that by noising Canvas pixels to prevent scripts from obtaining the browser identifiable data, which is otherwise available by reading the Canvas pixel data. And for fonts, we're limiting access to the default OS shift fonts. So ultimately, a user is less identifiable, and we're also reducing variability that the user installed fonts introduce. So thank you for attending our talk. Hope you guys learned a lot. I'm Tanushree.
John.
Feel free to reach out to us if you want to know more about our work or would like to chat. I'm not sure if we have enough time for questions. Maybe like a minute or two.
Yeah, we have like a minute.
Yeah.
We can start with
Yeah, how do we-
yeah, so.
For John,
Yes.
in your demo, you were providing the value for both the noise and unnoised. Providing access to the unnoised value seems to defeat the purpose of having
Yeah.
noised.
So in this particular demo, we have to noise it at least one time. That's the hash value you're seeing, but the noise version that you see in the demo, is actually like double noise. So we have a get image data that is putting it in the canvas, and then we're receiving the 2 data URL from that. So you're performing 2 readback operations, and we're nosing it twice, essentially. That's just for the sake of the demo. Unfortunately, we obviously can't just disable it like in the middle of the noising, but that's essentially how it works.
Got it. Thanks.
Hi, my name's Ken. I work on Canvas-related APIs. I'm super concerned about websites being broken by having noise added to readback operations. And the APIs that I work on, it's not necessarily going to be just rendered information. It could be, GPU computed values, in which case if you twiddle bits on it, you're going to get like a floating point value that's way different than what you actually intended. Can you describe what you're intending to do to mitigate or eliminate website breakage with this intervention?
So I'm not sure how much I can say of what we're intending to do, because there's a whole bunch of legal stuff there, but that's something that we've kind of noticed. There can be a lot of breakage, and some of the discussions we had early in the design is that we're going to expect breakages, especially in floating point values. I guess we can't. I hate to say it, we can't really say too much on what we're going to do and what we're intending to do, but just so you know that we have looked into it, we have considered this. But if you want to talk one-on-one, we can quite happy to do that.
Okay.
There's a talk on the algorithm later. So
So I'm assuming that for Canvas, the differences between GPUs is because of MSA, right? Multi-sample anti-aliasing and those kinds of things. So couldn't you do the same thing with WebGL? I could render a circle.
Sunny. I'll make them.
And the readback wouldn't be like a web API, right? It would be like a GL API, fix copying to a buffer and
Sorry, go ahead. Yeah.
you could copy to a WebGL buffer, and those operations are so generic that you don't know if it's for reading back the contents of something or some like Ken mentioned, right? You have compute-based algorithms, you have vertex feedback and those kinds of things. So you can't really tell that something should be noised or not.
Right. So WebGL is something we've been kind of putting off to the side for now. It's something we're going to look into the future, but right now we're kind of just looking to the canvases. Actually, if you want to follow up with me, feel free. I can send you to the person who's working on the WebGL work. But yeah, so super unsatisfying answers.
Have you considered doing it at like the scale level instead of doing it after the fact and just always noising, and that way you don't have to do an operation later?
By the scale level, we might end up breaking more than we intend to. That's the problem with the scale doing this at the scale level.
But what if it was like within the range of two different GPUs, essentially, like a very small range, enough to give it a different hash?
Like, I guess, like, could you give me, so like, let's say device one has like this GPU and device two has this other GPU, and then the variations between the two GPUs actually are different.
And you wouldn't consider it broken between one device and another device, right? So if you did just a very small, subtle noise and did that always, you wouldn't necessarily have to do it after the fact, maybe.
I see. It's just a different, so just so I understand, you're trying to do the intervention at a lower level.
Just always do the intervention. Every time it draws a circle, it's adding some sort of noise.
Then I think in that particular, if we're always doing noise like unconditionally, then that could end up breaking more than we would intend to. Because the idea here is that we want to noise very lightly, such that it's unnoticeable to us as humans, but like but to the machine, obviously, it'll be different. But in that particular case, we would need to look more into the implementation details in that particular case. For now, the simplest use case for us is to do it after we render it, and then only noise when we're pretty sure that it is trying to fingerprint in this case. It's really just like a trade-off between user experience and then actually privacy concerns. Okay.
Do you want to cut off?
Yeah, well, let's finish.
We have time for one more question. I think we're like 4 minutes over right now. So yeah, go ahead.
I'm just thinking like big picture, long term. What's like this feels like it's an architectural bug that the GPU is leaking its model information in the rendering, right? Is there a path? I'm looking at Candy, like is there no path to standardize on this and say like, or at least parameterize?
Not just MSAA, there's tons of other discrepancies between GPUs. Even texture sampling is different between GPUs. That we've discovered recently through the Web GPU Conformance Suite. I don't think that you're going to achieve high performance and also get uniform rendering across GPUs. I don't know how to get there. I'd like to discuss whether Canvas is actually a primary leaker of bits of entropy, or whether we should be going after other parts of the web platform that are leaking more bits and would be more fruitful avenues that carry lower risk of actually breaking web content.
Yeah.
I don't know if there's time. How does this affect benchmarks? Like a lot of Canvas benchmarks be affected with this, like motion mark, for example.
Let's see. Sorry, could you repeat the last part of your question? I didn't quite hear it.
So motion mark is one of these browser benchmarks. They rely on Canvas APIs. I think some of them that you listed.
Yeah.
So have you measured, or is there?
Not particular yet. We're still in the testing phase to see what the impact is in this particular case. Like I said, we just released all these features last week. In terms of metrics and benchmarks and stuff like that, that's something we're going to look into the future.
So this could be released before the performance was compared.
No, we're going to probably do performance first before we release any of this.
The performance cost of when you draw something is only like one line of recording that this is something that needs protection, and so it's extremely minimal unless you actually read it back.
Yeah, Map does read that.
It does a lot.
Lots of feedback.
And there are thousands of benchmarks. There are thousands doing the same.
So it's already landed, right? So it would be seen.
It uses
Now.
software rendering for the canvas when it does feedback.
Okay.
So there's one motion mark benchmark which uses get image data, and that one we don't use the GPU canvas.
That's not.
Maybe that's okay.
I think there might be a little confusion here. This is not just going to affect everyone once 136 hits stable. It's behind a pinch flag. So to be clear, yeah.
It's only incognito, right?
Yeah.
Yeah.
Thank you.